Have you ever just looked around and wondered what makes everything, well, everything? I mean, the air, the device you're watching this on, you, it's all made of the same basic stuff. Today, we're going to pull back the curtain and look at the secret lives of the tiny particles that run the whole show, the electrons.
And here's the central mystery, right? Why is an element like sodium so incredibly reactive it literally explodes in water, while neon is so chill it just glows? Why are some elements constantly trying to hook up and form molecules, while others are perfectly happy flying solo? It's all about their personality.
So what's the secret to an element's personality? It's their address. No, seriously. Where an element's electrons live inside the atom is the key to, well, pretty much everything it does.
So, to figure this all out, we're basically going to become atomic real estate agents. We need to find the specific address for every single electron, and that journey starts with the biggest part of that address, the city where it lives.
Okay, so every electron lives in what scientists call a principal energy level. Think of these as cities, numbered 1, 2, 3, and so on, starting right next to the nucleus. And just like in the real world, the farther you get from the city center, the more energy you have.
And here's where it gets cool. Just like bigger cities have more neighborhoods, the higher the energy level, the more types of neighborhoods, or sublevels you get. Level 1 just has one neighborhood, the S sublevel. Level 2 has an S and a P. Level 3 has S, P, and D. You get the idea.
So if the energy level is the city, and the sublevel is the neighborhood, then the orbital is the electron's actual house. Now, it's not a neat little path like a planet going around the sun. It's more like a cloud, a 3D area where there's a super high chance of finding that electron at any given moment. And check this out, not all houses are the same shape. The S orbitals is basically a simple, round studio apartment. But then you look at something like the D orbitals. Those are like weird, multi-level mansions. And the shape of an electron's house has a huge impact on how it can interact with other atoms.
All right, so we have the city, the neighborhood, and the house. But you can't just have electrons moving in wherever they feel like it. Oh no, there are rules. Think of them as the laws of atomic real estate, and every electron has to follow them.
The first rule is the Aufbau principle, which is just a fancy way of saying that electrons are lazy. They want to use the least amount of energy possible. So, they always fill the houses in the lowest energy neighborhoods first, starting from the ground floor up. They follow this very specific order: 1s, then 2s, then 2p, and so on.
Okay, rule number 2, the Pauli Exclusion principle. Any given house or orbital can hold 2 electrons, tops. And if you're going to have 2 electrons as roommates, they can't be exactly the same. They have to have opposite spins, which we show with one little arrow pointing up and the other pointing down.
And finally, there's Hund's rule. This is all about personal space. When you get to a neighborhood like the P sublevel, which has 3 houses all at the same energy level, electrons will each take their own empty room before they even think about pairing up. It makes perfect sense, right? Everyone wants their own room if they can get it.
All right, you ready? We've got our address system, we know the rules. Now it's time to put it all into practice. We're going to be atomic architects and build our very first orbital diagram from scratch.
It looks way more complicated than it is, I promise. It really just comes down to 3 steps. First, we'll draw the boxes for the houses. Second, we fill them from the bottom up, pairing up electrons with opposite spins. And third, we just make sure to follow Hund's rule for those last few electrons.
Easy. Let's try it with a real element, nitrogen. It has an atomic number of 7, which means it has 7 electrons we need to find a home for. So, step 1, we just draw out the available properties. 1 box for the 1s house, 1 box for 2s, and 3 connected boxes for the 2p neighborhood.
Okay, now we start moving our 7 electrons in. We follow the rules. The first 2 settle into the 1s orbital, 1 spinning up, 1 down. The next 2 move into the 2s orbital, same deal. Boom, that's 4 electrons housed, 3 more to go.
So what do we do with the last 3? Remember Hund's rule? They want their own space. So 1 electron goes into the first 2p box, the next goes into the second box, and the last one goes into the third, all with the same spin. And that's it. We've just perfectly mapped the complete address for every electron in a nitrogen atom.
Now I know what you're thinking. Do I really have to draw this out every single time for every element? Well, what if I told you there's a giant cheat sheet that's been hiding in plain sight this whole time? Because the periodic table, it isn't just a list, it's a map. Just look at this. This is amazing. The entire periodic table is organized into these blocks that perfectly match the sublevels we just talked about. Those first 2 columns, that's the S block. That big chunk on the right, the P block. The metal's in the middle, the D block. An element's location on this map literally tells you the neighborhood its most important electron lives in. And you can see it right here. Lithium, first element in the S block, has its last electron in a 2s orbital. Then you jump over to boron, first in the P block, and its last electron is in a 2p orbital. And hey, look, there's nitrogen, right where we'd expect it, with its last 3 electrons filling out the 2p sublevel. It all just clicks into place.
And that's really the whole point of all this. An element's address, its electron configuration, is what defines its entire personality. It's the code that tells you if it's going to be reactive or stable, who it's going to bond with, and who it's going to ignore. It is the secret to, well, everything.
So now you have the key. You can read the blueprint for pretty much any atom. But I want to leave you with one last question. If these electron houses are really just clouds of probability, what do you think happens when the clouds from 2 different atoms start to overlap? What kind of new things could they build together?